Ever stop to wonder about the invisible architecture behind the digital world? How does WhatsApp handle billions of messages, or Netflix stream perfectly to millions simultaneously without just, collapsing?
Yeah.
Or even how Amazon processes, 100,000 orders every minute on Prime Day? It's kind of amazing.
It really is, but it's definitely not magic. It's the result of very careful planning and engineering. It's system design.
System design, exactly what we're diving into today. We've got quite a stack of sources here, everything from like foundational articles and tutorials to community discussions and even a recent trends report.
Right. And our mission in this deep dive is basically to take these sources and unpack them for you. We want to give you a clear, concise, and hopefully genuinely engaging look at what system design actually is.
And why it's so important.
Exactly. Why it's absolutely essential in today's tech landscape, the fundamental concepts and techniques involved, and how it's being applied and evolving with new stuff like the cloud and AI.
Think of this as getting a shortcut to understanding the blueprints, maybe. The blueprints behind the complex digital systems you interact with every single day.
Yeah, that's a good way to put it.
So let's jump right in. What do we mean when we talk about system design? Like, what is it, really?
Okay, so at its heart, system design is the process of taking a set of requirements, essentially, what users need the system to do, and creating a detailed plan.
A plan.
A detailed plan, yeah. It defines the overall architecture, the individual components or modules, how they'll talk to each other through interfaces, and how the data will be structured and handled. It's turning those user needs into a concrete blueprint for actually building the system.
Okay, so it's like the detailed drawings you'd make before constructing, I don't know, a complex machine or even a building.
That's a pretty good analogy, yeah. And it's important to note the relationship, but also the difference between system design and system architecture. Architecture is often seen as the higher level view.
The big picture.
The big picture, exactly. The overall structure, the major components, how they relate at a broad level, sort of like planning out a whole city.
Right, the city plan. And system design then gets down to the specifics.
Yeah.
Like the detailed plans for the individual buildings within that city structure.
Precisely. Design is more focused on the detailed implementation plan for those individual components and how they actually function together. Both architecture and design are crucial stages, of course, but they operate at different levels of detail.
Okay.
And the overarching goal for any system design, really, is to ensure the final system is well organized, efficient, reliable, and capable of handling the required workload, basically, that it's scalable.
Got it. The detailed how, based on the high level what and where.
Mm-hmm.
So why is this skill, this process, so incredibly important in the tech world right now? What's the big deal?
Well, our sources really hammer this home. First off, it's absolutely vital for career progression in tech. As you move into more senior or leadership roles, the ability to design complex systems becomes, well, paramount. Many experienced engineers find that system design knowledge is a key differentiator.
And not having it can hurt.
Yeah, lacking it can even lead to unexpected outcomes in interviews, sometimes described as a down-leveling.
Yeah.
It's often where you demonstrate the ability to think about impact beyond just, writing code for a single feature.
So it's the difference between building a single sturdy wall and understanding how that wall fits into a skyscraper that needs to withstand earthquakes and wind, maybe.
Exactly that. A perfect analogy. And that understanding is fundamental to building solutions that can scale to handle massive traffic or data.
Right, like the Amazon example.
Exactly. That Amazon Prime Day example you mentioned, 100,000 orders per minute. That kind of scale isn't accidental. It requires deliberate design choices using techniques like load balancing to distribute traffic, distributed databases to manage huge volumes of data, and caching to speed up access to popular items. Without a solid design incorporating these, the system would simply buckle under that kind of load.
So you have to be prepared for the stampede before it happens.
You really do. And it directly impacts the bottom line, too. Well-designed systems are significantly more cost-efficient.
How so?
Well, the sources highlight YouTube's use of edge caching as a fantastic example. By storing popular videos on servers physically closer to users, that's a content delivery network strategy, they drastically reduce the distance data has to travel.
Which makes it faster for me watching cat videos.
Faster for you, exactly. And it lowers latency, and it saves YouTube millions of dollars annually on bandwidth costs. Good design isn't just a technical luxury, it's a business necessity.
Performance and cost savings, that's a pretty compelling combination.
Absolutely. And for anyone in leadership roles like a CTO or a tech lead, a deep understanding of system design is just non-negotiable.
Makes sense.
It informs critical decisions about infrastructure investment, scalability strategies, security architecture, and ultimately, how technology supports the overall business goals. It also plays a crucial role in communication.
Oh, yeah.
Yeah, it acts as a kind of single source of truth that translates technical requirements into a clear plan understood by both developers and stakeholders.
And as more and more systems move to the cloud, I imagine design becomes even more complex and critical.
Oh, absolutely foundational. Designing effectively for cloud environments is key to actually realizing the benefits the cloud promises: scalability, reliability, performance, security, cost efficiency.
Yeah.
You have to design for the cloud's distributed nature and the services it offers.
Right, you can't just dump your old stuff there.
Not if you want it to work well, no.
So how do you actually start building one of these blueprints? What are the initial steps and core ideas in the design process?
Okay, so based on the sources, the process typically kicks off by clarifying the scope.
Yeah.
This is where you really dig into the use cases, who is using the system, what are they trying to achieve.
Understanding the why.
Exactly. And defining the constraints. This is crucial at scale. What kind of traffic volume are we expecting? How many requests per second? How much data will we store? And what are the patterns? Lots of reads, lots of writes, or a mix.
Got it. Understanding the problem and the potential load first, that seems vital.
It really is.
Huh.
Once you have that clarity, you move to creating an abstract design. You start breaking the system down into logical modules or components.
Okay.
You think about the relationships between these components, things like whether you need a single instance of something accessible everywhere, like a singleton, how objects are composed with others, or if one type inherits properties from another. And right alongside this, you design the database schema, how the data will be organized and stored.
This sounds like the initial high-level design phase, the HLD.
It is, yeah. High-level design is the overall structure, the main components, and how they interact. Low-level design, or LLD, then drills down into the specific details of implementing each individual component.
The nitty-gritty.
Right, the actual code structure, data structures, algorithms within that specific component.
So HLD is the city layout. LLD is the detailed floor plan for, say, the library within the city.
Perfect analogy. And a key part of this whole process is also proactively identifying potential bottlenecks.
The weak points.
Exactly. Where might this system hit limits? Maybe the database can't handle the right volume, or a single server becomes overloaded with requests. Identifying these potential points of failure or slowdown early allows you to design solutions for them.
Like adding a load balancer.
Like adding a load balancer or distributing the database, yeah. While also considering the potential downsides or complexities those solutions might introduce. There are always trade-offs.
So spotting potential trouble spots before you even build. Smart.
Right. And stepping back slightly, it's also worth distinguishing system analysis from system design. Analysis is the phase where you gather and understand all the requirements, talking to users, understanding the business needs.
Okay.
Design is where you take that understanding and create the plan to meet those requirements. Analysis really has to come first.
Understand the need thoroughly, then draw the plan. Makes sense.
Yeah.
Okay, once you have this initial blueprint, what are the powerhouse techniques that designers use to make sure these systems can actually handle massive scale and stay resilient?
Right. This is where the real toolkit comes out. Scaling is fundamental, obviously. And there are two core approaches. Vertical scaling,
Okay.
which means making the existing machine more powerful by adding more CPU, RAM, or storage, more horsepower.
Beefing it up.
Exactly. And then there's horizontal scaling, which means adding more machines to share the load.
So vertical is upgrading a single server. Horizontal is adding more servers to a farm. Horizontal feels more relevant for massive web services, right?
Often, yes. Horizontal scaling is really key for many large distributed systems. And when you have multiple machines, a load balancer becomes pretty much essential.
Okay, the traffic up.
Yeah, good way to think of it. This component sits in front of your servers and intelligently distributes incoming traffic across them, preventing any single server from getting overloaded. This improves performance, makes your system more reliable if one server fails, and increases overall availability. You can have them as hardware appliances or, software.
So it's like directing cars to different lanes on a highway to prevent jams. Very smart.
Exactly. Now, to make things faster and reduce the load on your backend, caching is indispensable.
Caching, right. Heard that mentioned.
Yeah. Caching involves storing frequently accessed data temporarily in a faster, closer location. This could be application-level caching right in your code, database-level caching built into the database system itself, or dedicated in-memory caches like Memcached or Redis for extremely low latency.
Super fast access.
Super fast. You might also cache things like pre-calculated results or pre-generated indexes to speed things up.
Like keeping copies of the most popular products or pages right where they can be accessed instantly.
Precisely that. Database techniques are also critical for both scale and reliability. Database replication, for instance, creates copies of your data on multiple servers.
This is safety.
Well, yeah, it's great for availability. If one database server goes down, others have the data. It also helps with consistency if you design it right. And for truly enormous data sets that just won't fit on a single machine, you use database partitioning or sharding.
Sharding, that sounds complicated.
It can add complexity, yeah. It means dividing a large table or data set across multiple database instances, like splitting that giant library we talked about into separate buildings, maybe.
Oh, yeah.
You have to decide how to split the data, that's your sharding key, and figure out how to query data that might be spread across multiple shards. But it's often a necessary technique when a single database instance just can't handle the volume or the query load.
Makes sense for massive scale.
Definitely. Another powerful technique, especially in systems broken into many smaller parts, like microservices, is asynchronous communication, often using message queues.
Okay, how do message queues help design a better system? What do they do?
Right, so message queues like SQS or RabbitMQ act as intermediaries instead of one component calling another directly and waiting for a response.
Which could take time.
Exactly, it could block things. Instead, the first component just sends a message to the queue saying, hey, do this task. The second component picks up the message from the queue when it's ready. This decouples the components.
Ah, so they don't depend on each other being available at the exact same moment.
Precisely. The sender doesn't have to wait, which improves responsiveness. And crucially, if the receiver is busy or temporarily fails, the message just sits safely in the queue, waiting. This isolates failures. One component going down doesn't necessarily break the whole chain, and it helps handle bursts of traffic by sort of smoothing out the load.
Ah, okay. So it has resilience and flexibility. I can see that.
Exactly. And those content delivery networks, CDNs, we touched on with YouTube, they're a prime example of caching and distribution. But specifically for static content like images, videos, website assets, they place copies of this stuff on servers distributed globally. When a user requests content, it's served from the geographically closest server, minimizing latency and reducing load on your main origin servers.
Putting content closer to the user physically makes sense.
Yep. And for systems with many different backend services, especially in a microservices architecture, API gateways are a really common design pattern.
What's their role?
They act as a single, unified entry point for all client requests. They can handle things like authentication, routing requests to the correct backend service, rate limiting, maybe transforming requests. It provides a layer of abstraction and centralized control.
Like the main entrance to a large office building, directing visitors to the right department.
That's a great analogy. Yeah, right. And sort of guiding all these specific techniques are broader design patterns. These are reusable solutions to common problems that provide proven templates for building robust and maintainable software.
Tried and tested recipes.
Kind of, yeah. Increasingly, designers also rely on tools like containerization, thinking about how applications will be packaged using things like Docker, and orchestration platforms like Kubernetes to manage deploying and scaling those containers across different environments. This is huge in the cloud, of course.
Docker and Kubernetes are definitely foundational for modern deployments. You hear about them everywhere.
They really are. And for really heavy analytical processing on huge data sets, sometimes techniques involving frameworks like MapReduce might come into play, breaking down massive computations across many machines.
Wow, that's a comprehensive toolkit. Now, let's shift focus to the cloud specifically. You mentioned effective design is critical there. How does building in the cloud influence the design process and how you apply these techniques?
Well, the cloud fundamentally changes the playing field, right? Because you're building on a platform of highly available, scalable services provided by someone else, Amazon, Google, Microsoft, etc.
Right, you don't own the hardware.
Exactly. And effective system design is crucial to leverage these services correctly and avoid simply replicating the problems of, old on-premise systems, but now just running them in the cloud.
It's not just lifting your old servers and dropping them into Amazon or Google's data center, hoping for the best.
Absolutely not. That usually doesn't end well. You need to understand the different service models, infrastructure as a service, IaaS, platform as a service, software as a service, SaaS, and the deployment models like public, private, hybrid.
Okay.
These inform your design choices about how much you build yourself versus how much you consume as a managed service. You also have to design your networking carefully within the cloud provider's environment, thinking about concepts like virtual private clouds, VPCs, subnets, gateways, and peering to control security, connectivity, and isolation between your resources.
So these are kind of the structural elements the cloud gives you to build upon.
Yes, exactly. And the techniques we discussed. They're often applied in cloud-specific ways. Microservices are popular in the cloud partly because they map so well to containerization and orchestration tools like Kubernetes. Elasticity, the ability to scale resources up or down automatically based on load, is often a built-in feature via auto-scaling services. Designing with stateless components becomes easier and more important when virtual machine instances can appear and disappear automatically.
Right, you can't assume a specific server will always be there.
Exactly. Robust data management involves leveraging the cloud's incredibly wide variety of storage options, object storage, databases, data warehouses, plus backup services and integration tools. And cloud security best practices, from identity management, like IAM, to network security groups and logging, really need to be integrated into the design from day one.
So the cloud offers services that can make implementing these patterns and techniques easier, maybe. But you still have to do the hard work of designing the how and why it all fits together.
Precisely. And we see this in action with major players. Our sources point to Netflix, for instance, using AWS with a very sophisticated microservices architecture.
Yeah, they're famous for that.
They are. And they're also famous for pioneering chaos engineering, intentionally injecting failures into their production systems to test their resilience at scale. That, combined with a global distribution strategy, is a direct result of designing specifically for cloud-native reliability.
Chaos engineering, stress testing your system by basically breaking it on purpose. Wow, that highlights a real commitment to reliability.
It really does. Airbnb is another example.
Yeah.
They also heavily use AWS, designing for a scalable infrastructure supported by robust, continuous integration, continuous deployment, CI/CD pipelines for rapid updates.
They're getting changes out quickly.
Yes, and rigorous monitoring and cost optimization techniques like using spot and reserved instances to manage their cloud spend efficiently. That's part of the design too.
So designing not just for performance, but also for agility and cost control in the cloud.
Right. And Spotify famously migrated to Google Cloud Platform, or GCP. They leverage Kubernetes extensively for container orchestration, BigQuery for massive scale analytics on user listening data, and Kafka for real-time data streaming pipelines.
Different cloud, different tools, same principles.
Exactly. Each of these companies design their systems specifically to take advantage of their chosen cloud's capabilities for their particular needs and scale.
It's fascinating how these principles are applied at such massive scales. Beyond the cloud itself, what are some of the newer trends influencing how systems are designed today? Anything popping up in the sources?
Oh, yeah. The InfoQ Trends report in our sources highlights some really interesting shifts, and many of them are related to AI.
Not surprising.
No, not at all. For example, agentic AI is listed as an innovator trend. This is about designing autonomous, collaborative AI systems. The big design challenge there, the report notes, is trust.
Trucks.
Yeah. How do you design a system where you can actually verify and trust the decisions made by these independent AI agents, especially when they interact?
Designing for trust in automated systems. That's definitely a new frontier. Feels complicated.
It is. Small language models, SLMs, are also in that innovator space. These are more specialized and efficient compared to the massive large language models, LLMs, we hear so much about.
Okay, smaller AI.
Yeah, and from a system design perspective, they offer potential advantages in cost, speed, and the ability to deploy models on the edge closer to where the data is generated, rather than sending everything back to a central cloud service for processing.
So designing systems with smaller, specialized AI components placed where they're most effective.
Interesting.
Exactly. Retrieval Augmented Generation, or RAG, is a bit further along in the early adopter phase. This is a very common technique now to improve LLM output quality by giving them access to specific, relevant, often up-to-date external data when they generate a response.
Like feeding it company documents so it can answer internal questions accurately. Precisely. So this means system designers are now actively incorporating RG patterns into their architectures, designing components that handle that data retrieval and feeding it effectively to the language model.
Integrating internal knowledge into the AI's process, basically.
Right, and AI-assisted development is now firmly in the early majority. AI tools helping engineers write code. This raises design questions around ensuring code quality and consistency when different developers might be using different AI tools.
Yeah.
It also prompts considerations about how these tools might generate code that interacts with existing APIs that perhaps weren't originally designed with automated, maybe less predictable clients in mind.
So AI changing the development process itself impacts the design of the tools and the systems being built. A feedback loop.
Definitely. Shifting away from AI for just a moment, there's a growing trend highlighted around green software designing systems specifically to reduce their carbon footprint.
Ah, interesting. More than just cost.
Yeah, it goes beyond just optimizing for cost or even pure performance. It's considering where and when your code runs to potentially align with renewable energy availability, for instance, or processing data locally to reduce the energy spent on network transmission. It's integrating environmental factors directly into design decisions.
Wow, designing for sustainability.
Mhm.
That feels like a significant new factor for architects to juggle.
It is. Privacy engineering is another innovator trend the report mentions. This is about building privacy into the system design from the ground up, treating it as a core feature rather than an afterthought bolted on later.
Privacy by design.
Exactly. And this is particularly critical now with AI systems often handling sensitive data, raising complex new questions about data usage, storage, and transmission patterns.
Yeah, fundamental for user trust, especially with AI.
And one more interesting one. Socio-technical architecture. This is an early adopter trend, and it focuses on designing systems while explicitly considering the teams and the people who will build, deploy, and maintain them.
Designing for the humans involved.
Yes. It encourages architects to be facilitators, helping teams make good design decisions collaboratively rather than acting as bottlenecks who dictate everything. It also involves viewing internal platforms, the tools developers use as products, with their own users, namely the developers themselves.
So designing the human systems alongside the technical systems for better outcomes overall makes a lot of sense.
It really does. And just to touch on one specific area mentioned in another source, designing web applications involves its own set of very specific considerations. Security aspects like cross-origin resource sharing, CRS, implementing full text search efficiently, designing for offline support using things like service workers, making decisions around server-side versus client-side rendering, managing asynchronous loading of resources, and constantly trying to minimize network requests to make things faster.
Right, lots of specific challenges within that web domain. So a lot of layers and constant evolution in this field. We've covered the concepts and techniques. Let's maybe look at a few more specific real-world examples from our sources that really showcase these principles in action.
Yeah, these examples really bring it home. Think about PayPal using something called the actor model. It's a specific concurrency design pattern to handle 1 billion transactions a day on just 8 virtual machines. 8!
8 VMs for 1 billion transactions. That's astounding efficiency.
It's incredible resource utilization achieved through smart design. Or WhatsApp, which famously handled 50 billion messages daily with a core engineering team of only around 32 people, at least in the early days.
Wow.
Their intense focus on simplicity in design and using the Erlang programming language, which is known for concurrency and fault tolerance, were absolutely key to achieving that kind of scale with such a lean team.
So the design enabled efficiency of people as well as the machines. That's powerful.
Absolutely. Uber uses sophisticated geospatial indexing techniques in their system design. This is crucial for efficiently finding nearby drivers when you request a ride. And they handle something like 1 million requests per second just for that specific critical function.
1 million per second, just finding drivers.
Yeah.
Wow.
YouTube, despite its massive scale, relied for a long time, and maybe still does in parts, on MySQL databases combined with Vites, which is a database clustering system developed at YouTube. It helped them scale their relational database for billions of users, showing you can definitely scale even traditional technologies with the right architectural layers and design.
That's a great example of adapting existing tech through smart design, not just throwing it out.
Right. Stripe, the payment processor, uses idempotent APIs in their design. This is a really important technique where making the same API request multiple times has the exact same effect as making it just once.
Why is that important?
Well, it's crucial for preventing accidental double payments if a user nervously clicks a Pay Now button twice, or if a network request gets interrupted and automatically retried by the browser or app.
Ah, safety net. Got it.
Amazon S3, their cloud storage service, achieves what they call 11 nines of data durability. That's 99 point, then 9 more nines% durability.
11 nines. That's almost impossible data loss.
Through relentless design, focus on redundancy, storing multiple copies of data across different physical data centers with checks and balances. It's a core design goal met through massive redundancy.
Makes sense for storage.
Cloudflare, which handles a huge chunk of internet traffic, manages something like 55 million requests per second with just 15 Postgres database clusters, according to one source. That's incredible efficiency, likely achieved through very clever database design, extensive caching, and smart request routing.
Yeah, squeezing amazing performance out of relatively few databases.
And Meta, Facebook has spent years developing incredibly sophisticated strategies for achieving high cache consistency across their enormous, globally distributed infrastructure. Keeping cache data up to date everywhere at that scale is a major ongoing design challenge.
Those specific numbers and techniques really underscore the power of thoughtful design. And I know applying these concepts to problems like designing, say, a URL shortener, or a chat service like WhatsApp, or a social media feed, or a ride-sharing service like Uber. These are common topics in tech interviews, right?
Oh, absolutely. They are classic system design interview questions for exactly that reason. They force candidates to think through the trade-offs, apply these principles we've discussed, and articulate the pros and cons of different design choices under specific, often hypothetical constraints.
Right. They test your ability to actually use this toolkit.
Yeah.
Well, this has truly been a deep dive into the world of system design. Quite a journey.
It really has. We've covered what it is, essentially, that crucial process of blueprinting complex systems from requirements.
Yeah.
But we looked at why it's so critical for career growth, building scalable solutions that don't fall over, cost efficiency, and technical leadership. We walked through the core process steps from requirements to HLD and LLD and identifying bottlenecks. And we covered a lot of the foundational techniques designers use for scale and reliability scaling types, load balancing, caching, various database strategies like replication and sharding, asynchronous communication with message queues, CDNs, API gateways.
The whole toolbox.
Pretty much. We saw how these principles are applied and often enhanced when designing specifically for the cloud, looking at examples like Netflix, Airbnb, and Spotify. And we explored some of the exciting modern trends shaping the future of design, especially the impact of AI, but also things like green software, privacy engineering, and that socio-technical approach.
Understanding these concepts really does give you a powerful lens for looking at the digital world around you, doesn't it? Helps you ask better questions, maybe spot the clever engineering solutions hidden beneath the surface.
Absolutely. And maybe here's a final thought to consider as we wrap up. System design is clearly evolving beyond just, drawing boxes and lines on a technical diagram. It's increasingly about navigating incredibly complex trade-offs.
Trade-offs, yeah, that came up a lot.
It did. And they aren't solely technical anymore, like the classic tension between consistency and availability in distributed systems, the CAP theorem. Modern design requires balancing performance, cost, security, and privacy, and now environmental impact.
Right.
And even how the system structure supports the people who build and maintain it.
That's a lot to juggle.
It is. And as we design more autonomous systems using things like those AI agents we mentioned, perhaps the fundamental challenge becomes, how do we architect these systems in a way that ensures we can genuinely trust the decisions they make, especially when they operate without constant human oversight? It adds this whole layer of ethical and trust-based design that wasn't nearly as prominent even just a few years ago. Food for thought.